cut through the noise and pull out those essential nuggets, really giving you that shortcut to being well informed. Today we're taking quite a journey, starting with something super familiar like guitar string vibrating, and then leaping really into the perplexing world of quantum mechanics. Yeah, our mission today is to unpack how this idea of a standing wave isn't just some, handy analogy for the quantum world. It's actually a direct mathematical blueprint. It connects classical physics right to the core nature of reality down at that subatomic level. So get ready for some hopefully aha moments that might just reshape how you think about waves and particles and even observation itself. Okay, let's ground this first, something we can all picture. That vibrating string, maybe on a guitar, or think of an organ pipe. It looks like it's just oscillating in place, right? A standing wave. But how does it actually form? What's going on there?
Right. Well, what's really fascinating, I think, is that a standing wave, fundamentally, it's an interference pattern. It's not like a regular traveling wave that, carries energy from A to B. A standing wave happens when you get two waves, identical frequency, identical amplitude, but they're traveling in opposite directions, and they just constantly overlap. Imagine like a wave hitting a boundary, a wall, and bouncing straight back on itself. That's the kind of interaction we're talking about.
So it's less about energy moving along and more about these patterns emerging because waves are crashing into each other, adding up in just the right way.
Exactly. That's the principle of superposition right there. The total motion, the net displacement at any point, is just the sum of what each individual wave is doing. And mathematically, this actually lets you write down an equation that neatly separates the wave's fixed change in space from its rhythmic oscillation in time. And the math clearly shows, crucially, there's no net flow of energy along the string in a standing wave.
Okay. And within that pattern, there are these really key features, right? The nodes and antinodes. What are those exactly?
Yeah, nodes are the points that just stay perfectly still. They're permanently at rest. Those are the spots where you have complete, persistent, destructive interference. The two waves always cancel each other out completely. And mathematically, these nodes end up being spaced exactly half a wavelength apart. Antinodes, then, are the opposite. They're the points of maximum wiggle, maximum displacement. That's where constructive interference is constantly amplifying the oscillation. And interestingly, all the points within one loop, between two nodes, they all move together in phase, but they're perfectly out of phase with the points in the next loop over.
Right, so if the ends of a guitar string are fixed, they have to be nodes. This starts to hint at something really big, this idea of quantization. How do those boundaries actually dictate the notes the guitar can play?
That's a really profound point. Why do musical instruments make specific notes? It's precisely because their physical boundaries impose very strict conditions. For a string fixed at both ends, like you said, those ends must be nodes, points of zero displacement. And that seemingly simple requirement, it actually dramatically restricts the wavelengths that even allow to exist stably on that string. It forces them into a discrete a quantized set of values, only wavelengths that fit perfectly, with an exact integer number of half-wave lengths fitting across the length of the string. Only those are allowed as stable vibrations. We call them normal modes or harmonics.
So hang on, quantization, this idea of things only being allowed to have specific discrete values. It isn't just some weird quantum thing. It actually pops up naturally in classical physics whenever a wave is confined.
Precisely, yes. Yeah. This classical example is such a powerful conceptual bridge, actually. The physical confinement, the box or the string ends, it acts like a filter. It only lets certain integer-related modes, these harmonics, exist. And this sets up a really critical theme for our whole discussion. Confinement naturally leads to quantization. That holds true for guitar strings, and as we'll see, it holds true for subatomic particles too.
Okay, seeing it in a guitar string is one thing, but now we make the jump. We go from the tangible world to the abstract subatomic realm where, classical certainty just breaks down. It becomes about probability. How is information about a particle even encoded in quantum mechanics?
Right, so in quantum mechanics, everything we can possibly know about a system is contained in its wave function, usually written as psi, like that Greek letter. Now, the key thing, and this trips people up, is that unlike a classical wave, it's not a physical displacement. You can't, point to it in space.
Yeah.
It's an abstract mathematical function. It involves complex numbers, even. Think of it more like a wave of information or a wave of possibility, maybe, rather than a wave moving through something physical.
Okay, that's definitely abstract. So if someone's trying to picture this wave function, what's the biggest misconception? And how do we get from that abstract math to something physically meaningful?
Yeah, the biggest mistake is trying to visualize it like a water wave or a ripple. It's not like that. Its physical meaning comes from something called the Born rule. You take a wave function, you find its absolute value, and you square it. That number, A2, gives you the probability density. It tells you the likelihood of finding the particle at a specific position if you were to measure it. So quantum mechanics doesn't say the particle is here. It says, here are the probabilities for where you might find it. And of course, since the particle has to be found somewhere, if you add up all those probabilities over all of space, they have to equal 1 or 100%.
Okay. And just like with classical waves, superposition is fundamental here too, right? But I get the feeling quantum superposition is different, radically different.
Oh, absolutely. The Schrödinger equation, which is the fundamental rule for how the wave function evolves in time, is what we call a linear equation. And what that linearity means is if quantum system could be in state psi 1 and it could be in state psi 2, then it can also exist in any combination of those states.
At the same time?
At the same time, yes. Simultaneously, it's profound.
Yeah.
A quantum particle, like an electron, can literally be described as being in a superposition of, say, being in two different places at once. It exists in this combined state, this mixture of possibilities, right up until the moment you try to measure it.
Yeah.
The numbers in that combination, the coefficients, tell you the probability of finding it in each of those specific states when you do measure.
Wow. Okay, that's a massive shift from classical thinking. So if a classical wave's amplitude tells us about its physical size and its energy, what do these quantum amplitudes tell us? What are the key differences we need to keep straight?
That's a great question. So classical amplitude, real number, physical displacement, like wave height, and energy is proportional to amplitude squared. Simple enough. Quantum amplitude, the value of the wave function psi. It's a complex number. It has no direct physical meaning by itself. It's only when you take its absolute square that you get something physical, the probability density. Also, the energy of a quantum particle isn't directly tied to the amplitude of its wave function. It's related more to its frequency or how rapidly it curves in space. And here's a crucial one. A node in a classical standing wave, that point of zero displacement, that's a point of zero energy. But a node in a quantum wave function, a point where psi is 0, that's a point of zero probability of finding the particle there. But the particle itself still possesses its full quantized non-zero energy.
Zero probability, but it still has the energy.
Exactly. And another key difference, those quantum probability amplitudes, being complex numbers, allows for interference effects that just don't happen with classical probabilities. It's fundamentally different.
Okay, this is mind-bending. But it leads to the critical question. What actually happens when we try to observe or, measure a quantum system that's in one of these superposed states?
Right. So for every property you might want to measure, like energy or position or momentum, there are special states called eigenstates.
Yeah.
Think of them as the pure fundamental states associated with that property. If the system happens to be in an eigenstate of energy, for example, then measuring the energy will always give you one specific, definite value, the eigenvalue associated with that state. These energy eigenstates are often called stationary states because the probability density of 2 doesn't actually change over time for these states. The probabilities stay put. However, and this is key, a quantum system evolves in two completely different ways. When you're not looking, not measuring, the wave function evolves smoothly, predictably, according to the Schrödinger equation. Superposition holds, everything evolves nicely. But the moment you perform a measurement, say, you measure the energy of the wave function undergoes this sudden drastic change. It collapses.
Collapses.
Yes, it collapses. Abruptly and probabilistically from that superposition of multiple possibilities down into just one single eigenstate, the one corresponding to the result you just measured. This is sometimes called the projection postulate. The act of measurement fundamentally alters the state and destroys the original superposition.
Okay, let's try to bridge this. How does a really simple model, like the particle in a box, help connect these abstract quantum ideas back to our classical standing waves?
The particle in a box. It's such a foundational model in quantum mechanics. Really clarifies things. So imagine a single particle, maybe an electron, trapped inside a one-dimensional box with perfectly impenetrable walls. It can move left and right, but it absolutely cannot get out. We want to find its stationary states, the states with definite constant energy. To do that, we use the time-independent Schrödinger equation. Inside the box, we usually assume the potential energy is 0, which simplifies the equation quite a bit.
So the walls, the boundaries of the box, are they just as important here as the fixed ends of the guitar string were?
Absolutely crucial, yes. Since the particle cannot exist outside the box, think of infinite potential energy walls. Its wave function must go to 0 right at the walls. 0 must be 0, and if L at the other end of the box must also be 0. Those are our boundary conditions. Now, The general mathematical solution to the Schrödinger equation inside the box involves both sine waves and cosine waves. But applying those boundary conditions specifically, the 0, 0 condition forces the cosine part to vanish completely. And then the other condition, 0, 0, demands that the sine function must be 0 at x hello.
Wait, sin KL0? That sounds exactly like the condition we found for the allowed wavelengths on the guitar string. Is that just a coincidence?
Not a coincidence at all. That's the punchline. It's the crucial connection. That condition, sin KL, 0, means that k times L must be an integer multiple of pi. So KL equals n, where n can be 1, 2, 3, and so on. This directly determines the possible spatial shapes of the wave function inside the box. They must be sine waves of the form phen x equals a sin k equals L. These are precisely the shapes of classical standing waves on a string fixed at both ends. It's not an analogy, it's the direct mathematical consequence of applying quantum mechanics to a confined system. The math forces this standing wave solution.
Okay, wow. So the math itself forces the wave function to take the form of a standing wave. What does that then imply about the particle's energy?
Well, imposing those boundary conditions forces k, the wave number, to take only those specific discrete values, kn equals n to L. And since the particle's energy is directly related to k squared, E equals k22 meters, where n should be as Planck's constant and m is mass. This immediately leads to the quantization of energy. The particle can only have specific discrete energy levels. N equals n2, pt2, 2, a can 2, 2. Only these energies are allowed.
And what does that energy formula tell us?
It reveals several really key non-classical features. One, discrete energies. Obviously, only certain energy values corresponding to integer n are allowed, no energies in between. Two, zero-point energy. Look at the lowest possible energy state when n1. The energy E1 is greater than 0.
It can't have zero energy, even if it's trapped.
Never. A confined quantum particle can never be completely at rest. It always has this minimum zero-point energy. It's a purely quantum effect stemming from the wave nature and the uncertainty principle. There's always a sort of minimum quantum jiggle. And three, energy spacing. The energy levels get farther apart as n increases. They're not evenly spaced like rungs on a ladder. The gap grows quadratically with n2.
So just to be crystal clear, these standing wave solutions, the Kenner X, these are the energy eigenstates for the particle in the box, the stationary states.
Yes, exactly. Each specific standing wave shape IX corresponds to a single definite energy value n. If the particle is known to be in the state stun, then measuring its energy is absolutely guaranteed to give the result n. And because it's a stationary state, the probability density, nx2, remains constant in time. The probability pattern doesn't change. So this really confirms the central idea. The standing wave isn't just a helpful picture. It's the mathematically unavoidable form of the spatial part of the wave function for any definite energy state of a confined quantum particle. Confinement plus Schrödinger's equation equals standing waves and quantized energy. It's built in.
Okay, we've firmly established that the definite energy states, the eigenstates of a confined particle, are these standing waves, but quantum mechanics allows superposition. A particle can be in multiple states at once. So what happens if we superpose these standing wave states?
Right, so a perfectly valid general state for our particle in the box isn't just one of those pure SU states. It can be a superposition of them. Mathematically, we'd write it as a sum. X, Tx, C1, X, E, I, E1, T, plus C2, X, E, I, E2, Tx, and so on. Each Cn coefficient tells us, well, Cn2 gives the probability that if we measure the energy, we'll get the specific value n. So the particle can indeed be sort of partly in the ground state, N1, and partly in the first excited state, N2, for instance.
That's fascinating. Okay, but if each individual standing wave state, each eigenstate, is stationary, its probability pattern doesn't change over time. What happens when you combine them? Does the combined state just become a new, more complex static pattern?
No. And this is where the really interesting quantum dynamics come into play. A superposition of states with different energies is emphatically not stationary. When you actually calculate the probability density, x, Ti2, for a superposition state, like a mix of N1 and N equals 2, you find something extra. Besides the terms from each state individually, you get cross terms or interference terms. And crucially, these interference terms contain factors that explicitly depend on time. They oscillate back and forth with a frequency related to the difference in energy between the states involved, like E2, E1, like beat frequency.
An interference term that depends on time, what does that actually mean for the particle? Where we might find it?
It means the probability distribution itself is no longer static. Because of this time-dependent interference, the likelihood of finding the particle at different places inside the box changes over time. You can literally visualize the probability density sloshing back and forth inside the box. The particle might be more likely to be found on the left side at one moment and then more likely to be found on the right side a moment later.
Wow, so that's how change happens in the quantum world. Not by the particle moving in a classical sense, but by its probability distribution evolving dynamically, this sloshing.
That's a great way to put it. There's this beautiful hierarchy, really.
Right.
At one level, you have a single standing wave, an energy eigenstate. That state is itself a superposition, but it's a superposition of, say, two counterpropagating traveling waves, representing definite momentum states. And that specific superposition freezes the probability distribution into a static stationary pattern. But then at the next level, if you create a superposition of these static standing wave states, provided they have different energies, that superposition unfreezes the system. The interference between the components with different energy beats introduces that time dependence, creating real observable dynamics in where you're likely to find the particle. So yeah, a system in a single energy eigenstate is probabilistically static. Dynamics, change, movement in probability that arises from superpositions of states with different energies.
Okay, that's an incredible picture. The smooth evolution via Schrödinger, creating these sloshing probabilities from superposed standing waves. But then, let's revisit the elephant in the room. What happens when we actually look, when we make a measurement?
Right, so the system is in this superposition, maybe sloshing between E1 and E2 probabilities. You decide to measure its energy. The outcome you get will never be some kind of average or mixture of E1 and E2, never. Instead, the measurement instantly yields a single definite result. You'll either get E1 with a probability given by C12, or you'll get E2 with probability C22. And in that very instant of measurement, the wave function does that collapse we talked about. It jumps from being that continuous superposition into just the single eigenstate corresponding to the energy value you actually measured, we'll learn too.
So the Schrödinger equation describes the smooth sloshing, but measurement is this abrupt probabilistic jump that the equation itself doesn't describe. That's the core of the measurement problem, isn't it? It feels like two different sets of rules.
That is exactly the measurement problem. It's arguably one of the deepest, most perplexing, and still unresolved issues in the foundations of physics. How does this system, evolving smoothly as a coherent sum of possibilities, suddenly get forced to choose just one reality, one specific standing wave pattern, the moment it interacts with the measuring device? There's no consensus. Interpretations range from saying collapse is just a fundamental, unexplained process triggered by observation or interaction with a macroscopic system.
Like consciousness causing collapse, some people used to say.
Well, that specific idea is less favored now, but the core issue of what constitutes a measurement remains. Other interpretations, like many worlds, avoid collapse entirely by suggesting all possible outcomes actually happen, just in different splitting branches of reality. Yeah. But regardless of the interpretation, this discontinuous transition from a superposition of standing waves to a single standing wave upon measurement is a uniquely quantum phenomenon. It fundamentally separates quantum behavior from anything we see classically.
Okay, so the math of the standing wave is this amazing bridge, but the physics underneath is worlds apart. Can we just quickly recap the absolute key differences to keep in mind so we don't oversimplify the connection?
Absolutely. It's crucial to see both the connection and the chasm. Let's nail down the distinctions. Governing equation. Classical waves follow the classical wave equation. Quantum states follow the Schrödinger equation. Different math, different physics. Medium. Classical waves need a medium string, air, water. The quantum wave function doesn't. It exists in an abstract mathematical space, configuration space, no physical ether needed. Amplitude nature. Classical amplitude is real. Physical displacement. Quantum amplitude, psi, is a complex number. A probability amplitude. No direct physical meaning itself. Amplitude squared. Classical. Proportional to energy density. Quantum is probability density, Born rule. Totally different meaning.
And the energy at the nodes.
Right. Energy. Classical nodes have zero energy. Quantum nodes have zero probability, but the particle still possesses its full energy and superposition. Classical superposition of two traveling waves makes one static standing wave. Quantum has that hierarchy. Superposition of momentum states makes a stationary energy state, a standing wave. But superposition of those energy states makes a non-stationary dynamic sloshing state.
And finally, observation.
Observation. Classical observation is passive. You look at a wave, it keeps doing its thing. Quantum measurement is active. It forces collapse, fundamentally changes state, destroys the superposition. It's part of the dynamics.
What a journey, truly. So the connection between classical standing waves and these quantum energy eigenstates, it's way deeper than just a convenient analogy, isn't it? It feels more like a direct mathematical inheritance. The rules governing a simple vibrating string find their ultimate, deeper expression in the fundamental laws of quantum reality. That standing wave shape is just what naturally, inevitably falls out of the math for a confined quantum particle with definite energy. But wow, that shared mathematical form completely hides this enormous conceptual gap. The classical wave's size tells you about physical motion and energy right there. The quantum wave function's amplitude is this complete thing, and squaring it only gives you probabilities. And all the interesting change, the dynamics, comes from this weird interference between different energy states, this superposition of standing waves that has no real classical parallel, leading to that probability sloshing. So in the end, the standing wave is maybe the perfect starting point. It uses our everyday intuition to help us grasp why quantum energy is quantized in the first place. Confinement does it. But then exploring what it really means, the probabilities, the superposition dynamics, and especially that baffling collapse during measurement, forces us to leave behind the comfortable, deterministic classical world entirely. It's really a journey from the tangible to the purely probabilistic and abstract. So, what's the takeaway for you listening? Maybe it's that the fundamental states of our universe are, in a deep sense, written in this language of waves. What other classical ideas, things that seem solid and familiar, might actually have deeper quantum counterparts just waiting for us to find them through the math? And maybe, how much does our everyday experience, our macroscopic view, kind of blind us to this underlying, vibrating, probabilistic wave nature of reality that's playing out constantly, everywhere, shaping everything? Definitely something to mull over until our next deep dive.